Okay, we're now going to talk about the periodic review inventory management system, also called the P, T system. And we saw when we looked at the advantages of the continuous review QR system that we talked about how if we review inventory periodically, we can combine a lot of small orders into one shipment and optimize transportation costs. So that's this system. The main difference between the continuous review and the periodic review system is suggested by the name itself. In continuous review, we are always monitoring the inventory level, and as soon as it reaches the reorder point, we place the order of size Q. In periodic review, we are not going to continuously look at the inventory level. We're only going to look at the inventory level after a time period P passes. So if P is in days and it's 7 days, then let's say every Monday we look at the inventory and we decide what to do. If the period is a month, you can look at it on the first of a month, last day of a month, middle of a month. You pick a date and every month you look at it. Okay. Now we already looked at inventory position and we mentioned that inventory position includes the inventory on hand as well as the orders that have been placed but not yet received. They're in the pipeline. And then we also subtract any back orders because that's quantity we have promised to certain customers but we don't have right now. So when the new quantity arrives, the back order quantity will just go away and not be available for sale. So we examine the inventory position at fixed intervals of time P, and then we place the orders. So time between orders is fixed because every P days we place an order. Previously, time between orders was not fixed in the QR system because if sales happen slowly, you would take a long time to hit the reorder point and it will be a large time between orders. But if sales happen quickly, then you'd have less time between orders. Reorder size varies as the order is placed to bring inventory position to a target level T. Okay, this is in contrast to queue systems where the same order size of queue is always placed. So how much to order? T is the target level of inventory. So the order quantity at each time, whenever we examine inventory after P days, the order quantity is given by T minus the inventory position IP. Okay. And then when to order is answered by every P days. How much to order is answered by T minus IP in this system. This is a diagram showing you how inventory position and ordering works. The red line is the target inventory level that we'll learn how to calculate. Every P days, we place an order. So at this time, which says IP1 position, our P days have elapsed from the past, and our inventory position is on this solid blue line and is much lower than the red line. So this difference, the dotted vertical line, is going to be our order quantity Q1. And when we place the order, our inventory position jumps up, but not the inventory on hand because it takes L lead time days for the order to arrive. Now, as soon as we place this order, our second time period of P starts, or P countdown starts. And during this countdown of P days, after a lead time of L days, our order actually arrives and our inventory on hand jumps up. You see, whenever you see vertical jumps on inventory on hand, that's because some order arrived from the supplier. The size of the jump is going to be Q1, which was given by T minus IP on the day we ordered. So that day that we ordered, we picked Q1 on that day, and that Q1 quantity arrives after L days. Now, we started the clock or timer for P days when we placed the order. So when the timer expires after P days, we check the inventory position again. Remember, when we receive an order, the inventory position merges back to inventory on hand because there's no more orders outstanding. So the solid line inventory on hand is also my inventory position until this day when the P days elapses. On this day, I compare my inventory position with the target level T. There's a big, huge gap. So I place a large order of Q2 because order quantity is going to be T minus IP, which is this dotted vertical height. Obviously, again, the order does not arrive immediately. It takes L days to arrive. And then when the order does arrive, my inventory on hand jumps up by Q2, and inventory position and inventory on hand merge again because there's no more outstanding orders. And the same pattern repeats. So every P days we place an order for T minus IP. Now the thing to notice is, let's examine when we place the first order Q1 on this day. Okay. Whatever order we place today, that's going to arrive after L days. But other than this Q1 order, because we have to factor into the Q1 order the safety stock we need. So Q1, the quantity Q1 is based on the target level T, and T is based on the safety stock as well. So when we're thinking about figuring out T, we have to realize in any given order quantity like Q1, what do we need to include? Because that inclusion is going to come from T, because Q1 is simply T minus IP. So what we need to include in Q1 is the quantity we need to sell over the time period P, because if you don't order enough to sell over the time period T, then we can be in trouble. But here is the tricky thing that sometimes takes a while to understand. When I place the order Q1, I receive Q1 after L days. But when do I receive Q2? I receive Q2 from this day right here, the start. I receive Q2 after P plus L days. So if I make a mistake in Q1 or order too little, my chance to rectify that mistake in Q2, that rectification or that correction will arrive not after P days, but after P plus L days. Okay, so my Q1 must be sufficient to take me for P plus L days, because the next order Q2 is going to arrive after P plus L days. So what that kind of means is that the target level has to be high enough that whenever you place an order, because T really, T minus IP determines the order, T kind of determines like, how much inventory you're targeting. That target level must be high enough to protect me against demand variability over P plus L days, because whenever you place an order, if you make a mistake in that order, the correction happens after P plus L days. After P days, you place Q2, and then it arrives after L days. So the protection interval is P plus L days. In the QR system, the protection interval was only L. We only ordered safety stock. We only kept safety stock to save us over our lead time L. That is why safety stock was Z times sigma of DL T, sigma of demand during lead time. We only were concerned about variability of demand during lead time. Okay, so our protection interval for a QR system was essentially the lead time, because that's the only time for which we are concerned about the safety stock. But in this system, we need to have safety stock for P plus L days. That's our protection interval. So our safety stock is going to be Z times sigma D P plus L. So the standard deviation of demand during P plus L days. So demand during protection interval, the standard deviation of that times Z will give us our safety stock. So essentially, it's very similar logic to a QR system, except that trying to protect yourself over L days, you now have to protect yourself for P plus L days. Okay, you can imagine how this system actually converts to a QR system. If you start making P smaller and smaller, okay, so if P, let's say, was 30 days, now you make P 10 days, then you make it 5 days, you make P 1 day. At P of every single day, and if L is long, like 2 weeks or whatever, P plus L is approximately just L, and you're approximately at a QR system. Imagine you make P even smaller, so P goes to 0. As P goes to 0, it becomes a few hours or 1 hour or 30 minutes. You are essentially going back to a QR system. So this system, we think about it differently, because you check every P days, and then you have a target level of inventory. You don't have a fixed quantity Q, right? But if P goes to 0, it kind of starts behaving, especially for safety stock considerations, it kind of starts behaving close to a queue system. Now, the other thing to notice is that each time we check inventory, we order target minus the inventory position. So imagine if we placed order Q1 here, okay, that's what we're doing on the diagram, okay. Let's say our P was just 1 day. So right after we placed Q1, the next day we checked our inventory position. It's just slightly lower than target inventory level. So we would place a second order for a few items. Then the third day, again, our T and IP are different. Inventory position would jump up to T again, right? Because you place a small order. But then this another day passes will fall a little bit again because of 1 day of sales. Then again, you place a T minus IP order. So you'll end up placing many, many orders of tiny orders based on just 1 day of inventory used up if your P was less than L. So even though conceptually, I said if P goes to 0, we go towards a QR system essentially, or especially for the safety stock calculation, we don't use this system when P is less than L days, because then we end up placing many, many tiny orders and it doesn't make sense. So you want to use this system if you're fine setting P to a value which is equal to L or more than L. I mean, you can set it to less than L, but then you're placing many, many small orders, and that may or may not be good depending on where the supplier is, how the transportation works, and you can think about the transportation costs, right? And anyway, in the logistics course, we really bring these two things together and we look at the trade-off between inventory and transportation costs and how to optimize the total. So right now, I'm just pointing out to you that that your inventory management has implications for your transportation costs, but we're not going into detail because this is just an operations management course. In more advanced courses, you would do that. Okay. So usually, and the examples you'll see in the exam or homework will usually have P bigger than L or equal to L, so you kind of wouldn't have this issue of ending up placing many, many small orders. So let's look at the formulas. What is T? So we have to calculate just T because the order quantity Q, remember in the QR system, we have to do two calculations. You have to calculate Q using the EOQ formula and then calculate reorder point R using a different formula. So you have two formulas, EOQ and the reorder point formula. Okay, here we just need the formula for the target level T because the order quantity is determined by T minus the inventory position. So we just have one formula. Now, we may use some other formula to find P, what P to use, but P can often be set based on convenience. And, we'll talk about that. But let's look at the formula for T. So remember our protection interval is P plus L days. So the first part of T is just the average demand during the protection interval, which is P plus L. So we take the daily average demand, D average, and multiply by P plus L in days. If P plus L is in units of weeks, then this will be a weekly average demand. So the units of D and the protection interval must match. They must have the same time units. Usually we work in days, but you could work in weeks, for example. Okay. So the first part, D average multiplied by P plus L in brackets, because we must do the addition first and then do the multiplication. This part is just the average demand during the protection interval. And then you must do plus and add the safety stock. And the safety stock must be for the protection interval P plus L as well. So it's going to be Z times the standard deviation of demand during P plus L days. Again, you're going to have three scenarios. If everything is constant demand, constant lead time, which means you're not given any standard deviations in the question, then sigma P plus L will be 0. There's no variability in the system, so safety stock goes to 0, and T just becomes D average times P plus L. If you have variable demand, but a constant lead time, then we have a formula that is standard deviation of demand times square root of P plus L. This is very similar to the formula in the QR system if you set P equals to 0, because standard deviation of demand times square root of L was the formula in the QR system. So the only thing that changed is instead of L, we put in P plus L under the square root. Now, if both lead time and demand are variable, and how would you know that? You'll be given a standard deviation for the lead time as well as standard deviation for demand. You'll have this big formula, which is P plus L times standard deviation of demand squared plus the demand squared, the daily demand or the weekly demand, whatever, the small d demand squared, not the annual demand, the small d squared times standard deviation of lead time squared. Okay. So using the appropriate formula, given the situation you're in, you'll find sigma PL. You would find Z like before using norm.s.inv function in Excel, multiply Z by the standard deviation of demand during the protection interval to get safety stock. Then you would add to the average demand during the protection interval, D times P plus L. You'll add to that the safety stock to get T. Again, this slide is kind of repeated. We're showing you how to find Z. It's just in Excel, you do equal norm.s.inv and give it the cycle service level, which should be specified in the question. And we already discussed what the cycle service level is in the context of a reorder point. So we can just use that kind of discussion. It's a similar idea here. Just do the cycle service level means the same thing here, and we just put it into the Excel formula to get the value of Z. Now the question becomes, how do we figure out P? Now, sometimes P is just given in the question because it's a convenience type of factor. We want to place all the orders once a week. Maybe we are a retail shop or a convenience store, and every end of the week we go around, check our inventory levels, and place all the orders. That was often done before the age of computers, where people were checking inventory, writing it down by hand, placing orders, filling out a lot of paperwork, faxing like hundreds of orders, things like that. And then they would have a dedicated day of the week where they would do that, and then they would look at inventory again next week or after every 2 weeks or things like that. Now, with computers, when all of this can be automated, computers can have the inventory levels in the IT system, and then they can do all the calculations. They can even, sometimes if there's electronic ordering enabled with your suppliers, computers can just generate the orders, send them electronically to your supplier. So the convenience factor is not that important anymore, and transportation optimization decisions kind of dominate why you would use the periodic review PT system. Okay. So for example, if you're a store a little bit far from the distribution center, or you're a retail store, given the fleet size and the transportation optimization at the distribution center, DC might tell you, okay, we can give you a replenishment truck once a week. And you have to order 24 hours before so we can load up the truck properly. So that means basically you get one order per week with the DC. Even if you were to place multiple orders, they would all arrive after a week in the next week's shipment, right? So you might say, okay, 24 hours before the truck is going to come leave the DC, you run this PT calculation and you place all the orders with the DC. You could do a continuous review system, but placing orders earlier before that is not going to help you because all the orders get shipped once a week. Okay, so if we did have flexibility about setting the periodic level and we were to calculate it, one option is to find the economic order quantity Q star. And then the time between orders that the Q star implies, because whenever you calculate Q star, it implies a certain number of orders a year because annual demand is D, so big D. So big D annual demand over Q star gives you the number of orders per year, and orders are expected to be evenly spaced. So 1 over the number of orders per year is the fraction of the year between orders, or time between orders. If you look at time between orders using EOQ quantity, Q star over D, years, that's a fraction of a year, the capital D is annual demand. This is just equal to 1 over N, where N is the number of orders and N equals D over Q star, because 1 over D over Q star, algebraically, when you're 1 over a fraction, the fraction flips, and 1 over D over Q star becomes Q star over D. It's just 1 over N orders, where N is the number of orders implied by Q star. So this is the fraction of a year after which you must you're expected to place another order. And so We don't like working in fractions of a year. Like what is 0.05 of a year? Like you don't know immediately until you convert it to days or weeks. So often we'll take the time between orders, Q star over D years, a fraction, and convert it to weeks or days. To convert to weeks, multiply by 52. To convert to days, multiply by 365. So you can also do time between orders of EOQ equals Q star over D times 365 to get it in days. Okay, and then this would be your P. So you said P equal to this in weeks, so you can set equal to this in days, whatever you want P to be. It's a few days, you use days. If it's a few weeks, you might want to use weeks, right? So you said P equals to the time between orders implied by the EOQ calculation, okay? Let's do an example. So we have a bird feeder. Demand is normally distributed with a mean of 18 units per week and a standard deviation of 5. Lead time is 2 weeks, and there's no standard deviation given for the lead time. Business operates 52 weeks per year. Oh, by the way, I wanna say something here that you multiply by 365 days by default. Okay, but if the question says something like this, 250 working days in a year, then because you don't work on the off days, you can't place orders on the off days, then you may want to use this to calculate P in working days. So instead of multiplying by 365, you may multiply just by 250 or the number of working days, whatever the question tells you, and then the P, which will be set to this quantity, will be the number of working days between orders. Okay. Usually we don't like to do that because the lead time doesn't work in working days. Because if your order is on a ship that's sailing, the ship does not stop sailing on the weekend. So the lead time is usually not working days. Lead time is just days. And because you have to do P plus L, P and L must have the same units. Okay. So because it's hard to put L in working days, we keep P in just regular days as well. Okay, so you will not see me ask you a question where I give you the working days for a PT system. Okay, because you have to do P plus L and they must be in the same units. So we'll just do it with 365 days. Okay, but I just want to point out that if you did have a situation where lead time was somehow in working days or working shifts or something, and then you could have P in working days as well, theoretically, because the units match, everything should be fine, and then you'll just have the protection interval, everything is in working days, and you're just ignoring the non-working days. But usually transportation doesn't work like that. Even trucks, if you're shipping over truck, the truck will just drive on over the weekend too, right? So usually we don't do that. We just keep everything in days. Okay, so we are already given the EOQ quantity. The Q system called for a safety stock of 9 units for a cycle service level of 90%. What is the equivalent P system? It says round answers to the nearest integer, but round the final answer only. Do not round intermediate quantities. And do it in Excel so nothing gets rounded anyway until you round manually for the last final calculation. Even though the slides are for just, I don't want to show like 5 decimal places on the slide, so I just show like rounded off numbers on the slide. But you should solve problems in Excel. Do not round except the final answer based on the question's specification. That's how I expect you to do problems for the homework and exams. Okay, so average D is 18, lead time is 2 weeks. Sigma D is 5, sigma L is 0. So we're going to go to the second row here because we're not given sigma L, so we assume it's 0. And so we're going to use sigma D times square root of P plus L. If you were to use the third row formula and just put sigma L equals 0, we'll get the same formula as the second row anyway. So if sigma L is not given, you will assume it's 0, and we get to the second row because sigma D is non-zero. Okay. Okay, so our annual demand is going to be 18 units per week times 52 weeks per year, or 936 units per week per year. That's annual demand. P is given by the EOQ quantity, which is 75 divided by the annual demand of 936. 75 over 936 gives us a fraction of a year. Multiply by 52 weeks in a year to convert to weeks, and it comes out to 4.2 weeks. Okay. Now you would use 4.2 weeks in the rest of the problem on a homework or an exam, unless the questions explicitly ask you to round off the protection interval or the period, to an integer number of weeks. Because 4.2 weeks in practice can be tricky, because it will keep moving the day you place order. So 4.2 weeks from today might be 4 weeks and 2 days. Okay, so then you order on, let's say, a Wednesday, but the next time you do 4.2 weeks, you might have to order on like a Friday, and then the next time on like a Monday. So every 4.2 weeks you're ordering on a different day, which can be a little bit confusing. So which is why I'm, showing you that in practice you might round it to 4 weeks, but for questions on the homework and the exam, you should only round it to 4 weeks if the question explicitly asks you, okay, you should round P to an integer number of days or weeks. And sometimes the question might, because in real life we would usually do that. We don't like ordering every 5.7 days. We like ordering every 5 days or 6 days, right? So that will become 6 days. Okay, so we're going to use 4 weeks to find standard deviation of demand during the protection interval. P is 4, L is 2, square root times 5. 5 is sigma D, give me 12.25 units. CSL of 0.9 converts to Z of 1.28 something. So you'll use the exact value from Excel. And then safety stock becomes Z times sigma of P plus L, which is 1.28 times 12.25 or 15.68. Now remember, the question tells us in the QR system, we had a safety stock of 9. So notice our safety stock went up to 15.68 from 9 because we need safety stock for a larger protection interval. Before we needed safety stock only for lead time of 2 days. Now we need safety stock for 4 plus 2 days. So T is going to be average demand during lead time plus safety stock. Average demand during lead time will be the small d, 18 times P plus L, plus the safety stock, which will be 123.68 units. Because the question asked me to round to the nearest integer, I'll call it 124 units. So my inventory policy is reorder every 4.2 weeks, but I'm rounding it to 4. I'm taking that liberty, but you would only do that if the question asks you. Reorder every 4 or 4.2 weeks. Reorder quantity will be T minus IP, or 1.124 minus IP. IP will be whatever inventory position is at the time when I check the inventory to reorder. Let's look at another example. Our on-hand inventory is 10 units. That's physically on hand. We have that. T is 400. There are no back orders, which means we don't have any quantity promised to the customer already, but one scheduled receipt, which means order placed but not yet received. So it's scheduled to receive, scheduled receipt of 200 units. Now is the time to review how much should be ordered. So basically we have to find inventory position IP. T is given to be 400. The order quantity will be 400 minus IP. So IP is inventory on hand plus orders placed minus back orders. That's going to be 10 on hand plus 200 of scheduled receipts, which is orders placed, minus 0 back orders, 210. And then order quantity will be T minus IP, or 400 minus 210, or 190. So we will place an order for 190 units. So rather straightforward calculation, but I just want you to see that that's how we would do it. Okay. Now this is really important, finding the total relevant cost for a PET system, because sometimes you're comparing between systems. So for the same cycle service level, the same demand, same lead time, you might calculate what is the additional cost I have to pay if I move from a QR system to a PT system. So you calculate Q and R and you find the total relevant cost for a QR system using the calculations I showed earlier. And then you can find P and T and then calculate the total relevant cost for the PT system. PT system will have a higher relevant cost here because all we are factoring in is the ordering cost and the inventory holding cost. So the PT system will have higher cost in terms of inventory and ordering. Then you would compare this increase in cost from the QR to the PT system with the savings in transportation it might give you. And then you'll say, okay, I'll go for a PT system if the transportation savings are significant enough to pay me for the difference between the QR and the PT system. So to make a final decision in real life, you would factor in the transportation aspect, which we will show you how to do in more advanced courses, but just keep that in mind. And here we're just showing you the cost of the inventory and ordering, the holding cost and the ordering cost, and comparing them with these costs. Okay, so the total relevant cost will be the average inventory holding cost plus the annual ordering cost. Remember, the inventory holding cost is always a function of average inventory level. So what is the average inventory level of a PT system? That's going to be cycle stock plus safety stock. We already know the formula for safety stock because it's part of the T formula. If you look at the T formula, right, that has the safety stock built into it, which is Z plus sigma, the standard deviation of demand over the protection interval, and that time Z times that. So that is basically gonna be the safety stock, Z times sigma P plus L right here. Okay, and then the cycle stock is in the QR system was Q over 2, but now Q is variable. So on average, the size of the order is going to be average demand times P, because that's how much inventory you use up. So let's say you start with T, the target inventory level. That's how you start. You're going to on average fall down by D times P, daily demand average times P days. Then you'll go back up, then you'll fall down by D times P like that, right? And so the cycle stock is going to be D average times P over 2. Okay, so that's the on average the cycle stock plus the safety stock. That's your average inventory level. Average inventory level multiplied by capital H, which is the cost to hold 1 unit in inventory for 1 year, which is dollars per unit per year. Multiply by that to get the annual holding cost. Remember, if you're given small h, which is the percentage, like 20% of the item's value, then you'll multiply the small h by C, the item cost, to get capital H. So if small h is 15% and item costs $10, then H times C will be $1.5 will be capital H, because you spend $1.5 to hold 1 unit in inventory for 1 year when small h is 15% and the item value or cost is $10. Okay. So you can always get to small h by doing a big H by doing small h times C. So sometimes question will just give you the big H, dollars per unit per year. Sometimes they'll give you small h at a percentage, 15% of the item's value or cost, and you multiply the small h by C, the item's value or cost, to get the big H. So the first part of this formula should be very clear to you. Cycle stock level plus safety stock, put brackets around it, multiply by H to get the holding cost. Now we want the ordering cost. So ordering cost is going to be number of orders times S. S is the cost to place one order. So the number of orders is given by D over average demand times P. Notice that D average times P is kind of like our Q now. That's like our average order quantity. So we divide D kind of like by our average value for Q, the average order quantity, which is D average times P, to get number of orders. Multiply that by S, the ordering cost per order, to get the total ordering cost per annum, and then add the whole thing up to get the cost, which is always going to be dollars per year. The units of this cost are dollars per year. Is the annual cost. Okay. Okay, so the advantages of a PT system are it's convenient to place orders at fixed time intervals. Employees can schedule time to create all the purchase orders and so on. And then also your financial processing, your payment, your cash flow management. You know that at each once a week or once a month, you need to have that much cash flow to pay for the orders. If you're paying right away, if you're paying on delivery, then you can just add, see when the deliveries will also happen at scheduled time. Okay. It can be very convenient because let's say you're a retail store. Imagine getting shipments every day from the DCs, of small shipments every day of the week. You have to have receiving staff to receive and put these shipments away every day. But if you could do once a week, you'll pick the lowest traffic day for your store, which is like the off day, maybe it's Sunday, maybe it's middle of the week, and you'll schedule your DC delivery to just come once a week, where you bring up one big delivery once a week, and there's not a lot of customers around, so you can use your staff to offload the truck and put the product away in the retail shop. So, retail shop operations, DC operations, transportation things, a lot of things can be optimized a little bit more, or made more convenient at least, in a PT system. But it has higher annual inventory and ordering cost, inventory holding and ordering cost. So you have to kind of see if that increase in cost is justified. Items can be combined into one shipment. So if you're making many small shipments from the same geographic region, buying many things in small quantities, you can kind of club them into one shipment to have transportation economies of scale, to save on transportation costs. And you do not need to continuously monitor inventory. So even a small mom and pop store that doesn't have like advanced IT system, you're going to do something like this. And I've seen this being used. I met a person who used to run very successfully the convenience store at gas stations. And they were making a lot of money out of that convenience store. And they were using this system to manage inventory. They were basically using pen and paper. They would go around the store, look at the inventory, or go to their back store, look at the boxes of inventory of snacks and so forth, and kind of use this sort of periodic review system once a week to place their orders. Disadvantage is higher level of safety stock than a QR system, so higher inventory holding cost. Let's do a couple of self-checks to see if you've understood the concepts. So let's say my supplier becomes more reliable, reduces the standard deviation of lead time. So supplier and/or the transportation between me and the suppliers, the combination of that becomes more reliable. So my standard deviation of lead time, sigma L, falls. It decreases. What happens to my inventory? So cycle stock decreases is one option. Total inventory stays the same. Cycle stock increases. Safety stock decreases. Which option is correct? I want you to pause and think of the answer on your own, then play the video again and I'll tell you the answer. In this case, the answer is going to be nothing is going to happen to your cycle stock, because that doesn't depend on sigma L. Only safety stock depends on sigma L. Total inventory depends on sigma L because the average inventory level also has safety stock part of it, but it does not stay the same. When sigma L falls, the safety stock decreases. So D is the only right option, because safety stock formula has sigma L in it. If sigma L goes down, safety stock goes down. Okay, self-check 2. I ordered many items from a supplier in small batches, so my order quantities are small. Okay, which of the following is most likely true? I use EOQ only. I should use QR system. I should use PT system. QR is continuous review. PT is periodic review. I cannot use this system for small frequent ordering. So pause, again, think of the answer. Think of what we talked about as the advantages of the QR and the PT system and so on, and try to figure out the answer. Then unpause the video and then you'll hear the answer on the video too. Okay, so we should use the PT system. Remember we said the main advantage of a PT system is you could combine shipments. If you're placing many orders, each order has a small quantity, then those orders could be bashed or clubbed together into one shipment. And that's a big advantage of the PT system. So this question is basically giving you the advantage of the PT system. And if that advantage is there, it's most likely going to be the best system to use, will be the PT system given the options. So C is the right answer. Inventory for seasonal items, 1 period decisions. Now we're going to look at the problem of how much to order when we cannot get a replenishment, because till now we have looked at QR systems, PT systems. In both of them, ordering again and again is a key part of the system. In QR systems, you keep ordering whenever you hit the reorder point. In PT systems, every P days you reorder. But sometimes the selling window is very short. Think about items for a holiday, like Halloween decorations. You may sell Halloween decorations over a 1 or 2 month period, and then if your lead time from the supplier may be 2 months. So once the season starts, whatever inventory you've gathered, that's what you sell. There's no reorders during the selling season. The selling season is so short. winter jackets, fashion clothing with short life cycles, product life cycle, holiday merchandise like Christmas decorations, all of these face this problem that getting them produced exactly how you want and shipped to the right places takes a long time. And once you have an order quantity ready before the season starts, during the season you can't update that, you can't have new quantity arrive based on observing the sales of the season. Because once you observe the sales of the season, you place a new order, by the time the replenishment will arrive, it will be too late. So some goods have a short selling season such that an order must be placed before the selling starts. No reorders can be placed during the selling season because the lead time is too long, and any leftover inventory must be salvaged, sold at a loss at the end of the season. So if we have this sort of a setup, we can't use QR or PT systems or the EOQ formula to figure out how much to order. It's something called a one-shot or one-period decision or a news vendor model, because newspaper have this problem. Nobody wants to buy old newspaper because that's yesterday's news. And so the newspapers that you print for a day, you sell them in that day, and at the end of the day, you just kind of trash them or do whatever you can with them because the next day they're not going to be useful. Now, how do we figure out how much to order? So let's first think about what happens if you order too few or too less. If you order too little, so that our order quantity Q is less than the demand over that selling season or selling time period, so this capital D is not annual demand anymore here, because the selling season could be very short. Selling season could be a day, selling season could be a month, selling season could be 6 weeks. So this is just demand for the whole selling season. And it's not small d like demand per day, because we don't know the length of the selling season. When you know the context, you can figure out the selling season. But whatever the selling season is, this is D over the selling season. In a way, it can be annual demand if the selling season happens only once a year. So Halloween may have a selling season of 1 month, but if there's no sales outside that 1 month, D is the demand over the 1 month, but also the demand for the year, right? But the definition of D, capital D here, is demand over the selling time period or selling season. So if Q is less than D, if the quantity ordered is less than D, and obviously we can't get a replenishment, then we're going to have shortage. We're going to have sales that we could have satisfied if we had more inventory, but now we can't make those sales. So the shortage cost of having too little is the revenue per unit minus the cost per unit. Okay? Because you lose that gross profit from the sale because you didn't have enough inventory. Okay? This is the shortage cost per unit. And then how many units do you have a shortage for? That's the difference between D and Q. D minus Q is the number of units you could not sell because of lack of inventory. And per unit, the cost is C shortage, which is revenue minus cost per unit. If too much quantity is ordered, you're going to have leftover quantity. And then the cost of excess per unit will be the cost per unit that you pay to the supplier to acquire the unit minus the salvage value. The salvage value can be zero if there's nothing you can do after the season with it and you just have to kind of like trash it. And then sometimes you can sell them at a deep discount, so there's some salvage value. But what we're going to study, the analysis, it only works when the salvage value is less than the cost per unit. If you can still recover your cost and make some money, then you can. Then the problem is a little bit different, because now you can kind of still sell them outside the selling season for a profitable amount. So it's more like a continuous review or periodic review system where you can have sales over a longer time period, like the whole year. And so we don't study that. What we are studying here is the salvage value is so low that you're going to make a loss. The cost per unit will be higher. The cost of excess will be a positive number. You'll make a loss. It will be cost per unit minus the salvage value. So we need to minimize the expected total cost of excess and shortage. Now, through some mathematical analysis, we figured out that our profit is maximized if we pick our order quantity Q star such that the probability that demand is less than equal to Q star is equal to the optimal service level, which is given by the equation on the slide. The optimal service level is also called the critical fractile. So this is basically like a CSL value for the one period decision. It's kind of like a CSL value because it captures the same idea that this is the probability that inventory will be enough. Demand will be less than equal to the inventory value Q star. So we first calculate this probability and then we get to Q star. So the probability is given by CS, which is the cost of shortage per unit, divided by CS plus CE, where CE is the cost of excess per unit. On the previous slide, we already saw how to calculate CS and CE. Okay. If demand is normally distributed, we can find Q star using the normal probability distribution because we know probability that demand D will be less than equal to Q star equals optimal service level, which we already found using this ratio. Then in Excel, we can do equals norm dot inverse the service level that we found using this ratio, the number for that, comma, the average value for the demand and the standard deviation for the demand. This would give us the Q star, this Excel formula. Let's do an example. Okay, we sell winter jackets for a price of $180. The cost is $110. Unsold jackets are sold for a salvage value of $70. Notice that the salvage value is less than the cost, so we can use the model we just talked about. Demand is normally distributed with a mean of 3192 units and a standard deviation of 1181 units. And replenishments cannot be ordered because the selling season is very short, winter is short. How many jackets should we order in advance of the selling season so that we can maximize our expected profit? So first we'll find the cost of storage and cost of excess. Cost of storage is just the price minus the cost of the item, which is $70. That's the gross profit we make for when we sell any single jacket. The cost of excess is just the cost of the item minus the salvage value, which turns out to be $40. That's the value or money we lose if we order an extra jacket and we don't use it up, because we paid $110 to the supplier and now we can only recover $70 of that. So we lose $40. The optimal service level is CS over CS plus E, which is 70 divided by 70 plus 40, which is 0.636. Okay. And now we can find Q star. We can do it two ways. We know the mean of the demand and the standard deviation. So we can use this formula. See, the service level we got was 0.636. So we can go to this formula in Excel and do equals norm.inv and put in 0.636 for the service level, 3192 for the mean of the demand, 1181 or 1182, whatever the standard deviation was here, and Excel will tell us Q star. The other option is we can do this in two steps. We can use norm.s.inv with 0.63, the service level, like we did before, to convert the service level into a z-score. Okay, so we can do something like this, equals norm.s.inv and pass it our service level 0.636. And this will convert it to a z value. Okay, v value is number of standard deviations. It's a normalized value. This exact same thing can be done with this formula because this is equivalent to equals norm.s.inv of 0.636. Because when you specify a mean of 0 and a standard deviation of 1 in a norm.inv formula, that's exactly equivalent to norm.s.inv because the S stands for standardized, which means mean 0 and standard deviation of 1. That's what the S actually means. So these two are the exact same formula. Okay, in old Excel, there did used to be norm.s.inv, so we do this, norm.inv with mean 0, standard deviation 1. But then Excel added the .s.inv, and now we can just do that instead of having to pass in the 0 and 1. The z-score we get is 0.349. Remember, z-score can be negative, which is fine. If it's negative, use the negative value. So here z-score is positive, which means go 0.349 standard deviations above the mean. That's by the meaning of the z-score. So we take the mean plus the z-score times the standard deviation, we get Q star. If z-score was negative, then this would be a minus sign here because you'll get a minus z-score, and then you would get a value below the mean. And that can happen. Okay? When the cost of excess is very high, you want to avoid any excess, you get order below the mean. So that's our order quantity Q star. Sometimes you're not given a normal distribution for the demand. Okay. So in that case, we are given the probability distribution, the probability of different values of demand. So demand is 10 with a probability of 0.2, demand is 20 with a probability of 0.1, and so on. Okay. So if that is the case, okay, then what you want to do first is find the cumulative probability column. This column would not be given to you, but it's very easy to find. For the lowest level of demand has to be sorted from small to high values. Okay, small to high. For the lowest level of demand, that is the cumulative probability, because that's the probability that demand will be less than equal to 10, which is exactly 0.2, because demand can be 10 and there's no probability of demand being lower than 10, so that's 0.2. Then what's the cumulative probability demand will be less than equal to 20? That's going to be 0.1 times the previous cumulative probability. You add the 2, you get 0.3. Next row, you take the 0.2, you add the 0.3, you get 0.5. Next row, you take the 0.25, add to the previous cumulative probability of 0.5, you get 0.75. And last row, you take the 0.25, add it to the previous value, you get 1. If the probabilities are correctly specified, you would get the final cumulative probability to be 1, because that's the maximum value of demand. That's the max value. So probability that demand is less than equal to the max value of 50 is 1, because demand can be 50 or less. Okay. Once you get the cumulative probability column, then you'll find your service level SL star using CS divided by CS plus CE formula. And then you'll find that value in this column of cumulative probability values. Let's say your service level, the optimal value was 0.71. Now we have 0.5 and then 0.75. So 0.71 falls between these two values, so you just use the higher value. So we'll go with 0.75, and then the quantity to order is going to be 40, because 40 corresponds to 0.75. Okay. So let's do an example. So here we have our demand distribution, different demand levels and demand probabilities, and we have the $10 of profit per unit. This right here is revenue minus cost, which is the cost of a shortage CS. Okay. So we're just given CS directly instead of being given revenue and cost. And then this is CE, because this is the cost minus the salvage value. Okay. Okay, so our critical fractile, or the service level, will be CS over CS plus CE, which is 10, which is the profit per unit given in the question. CE is 5, which is the loss per unit given for excess items. That's the cost minus the salvage value. The ratio is 0.667. That's our optimal service level. Then we find the cumulative probabilities. For the first row is just that. For the second row is this plus this, which is 0.5. For the third row is this plus the 0.5. For the next row is 0.1 plus the 0.8, and so on. We find the cumulative probability column. Then we look up 0.667. That is between these two values. So we take the higher value, and 30, the museum should stock 30 units with a cumulative probability of being in stock of 0.8. Okay. So it's very easy The first step is always find service level optimal. Second step is if you're given a normal distribution, you can use equals norm.inv or use norms.s.inv and then multiply the z-score by the standard deviation and add the mean. Or you look up SL star in the cumulative probability column. Okay. So hopefully this made sense. If not, you can rewatch the video about the examples, or when you do the homework problems and you solve them, and watch the help video for that, it will make a lot of sense. But this is how we can convert the cost of excess and cost of shortage first to a service level, and then from a service level you look at cumulative probability column, or if it's a normal distribution, you use the z-score in the normal distribution to find the quantity to order. The quantity you figure out with this method is the quantity which optimizes your expected profit. Now remember that what we are saying is that when the service level is between two categories, you just go with the higher one. Sometimes you may want to compare expected total cost by rounding it down and up. So 0.667 can go to 0.5 or 0.8. You may want to check both in real life to see which one gives you less expected total cost. But for this course, we're keeping things simple. So when it's your service level, the optimal service level is between two values in the cumulative probability column, just round it up to the next highest value and use that. Okay. Okay, so that is the end of the inventory management lecture and the module. So that covers all the content we were going to do for inventory management here. And hopefully this was useful and a good basic level of knowledge, the essentials of inventory management, and then you need to know this to build on it in more advanced courses.